Bishop, welcome back for the second session this morning. So it's an immense honor and pleasure to introduce Fabrizio Catanese, who will speak on nodal surfaces.
Okay. Well, first of all, I would like to thank the organizer, Ludwig, and also for the opportunity of presenting some topic. So this is a quite general topic. It's a lot of things. I doubt I will be able to talk about everything, but it's a series of 4 papers which are related. And the new thing is the application of cohomology theory to nodal surfaces. And I intend particularly to concentrate on, well, since the title of the conference is periods and Shafarevich map, especially on the cake surfaces side. And I will use the beamer at some point. Maybe I'll do some picture on the board. Okay, this is a foreword which I borrowed from some colloquial talk. So this is really not for us like geometrists, but it's sort of something which I'd like to say. There are some students that think, oh, why do we polynomials? There are particular cases of analytic functions. And however, you know that preparation theorems of Weierstrass and Lagrange, they show that locally analytically differentiable functions, they behave like polynomials, and in fact, the local study is to prepare them as pseudo-polynomials. And in fact, maybe 50 years ago, probably, René Thom really thought of applying singularity theory to many fields different from mathematics. And I don't know how successful this was, but for me it was very interesting. And the last thing I'd like to say is that, well, I will read about many results for low-degree surfaces. On the other hand, well, as I learned from Pete, I mean, many things of local differential geometry and hyperlocal analysis, it's very important, the knowledge of polynomials of low degree. And the main morale, when I started this project, well, this benefited from COVID because I had nothing to do, and so this is more than 200 pages, something I thought I would never do. At a certain moment, I asked some computer, some coding theory experts, and they always say, "Oh, but we run a computer program." And well, computers are extremely helpful, but for me, they're more helpful to do like routine calculations. And because if the question to the computer and the computer gives an answer, and this answer is too long for me to be read and understood. If we go back, this is the same time, the same thing was occurring for mathematics of the 19th century. There were all these books and dog lists, and at a certain moment, this that's a mistake. I wrote 18th century mathematics, but I meant 1800. So this should be 19th century mathematics. And there was a development of precise abstract concepts, and like, you know, first issue being the notion of a vector space, which some physicists say was the only good thing which remained from Hamilton's work, but I disagree. So if a list is too long, well, what's the point? And so we should really evaluate theorems. And the goal is to have, if possible, it's nice to have a theorem which can be formulated in a few lines. And this is somehow what we understand. We should do mathematics according to our brain. So before enumerating solutions, we should understand what is the answer. Now, as I say, in this I will mostly concentrate on K surfaces. Afterwards, if there is time, I will explain the picture. So, one of the most famous applications of the theory of period maps is the Torelli theorem for K surfaces. And in this lecture, I will explain how to determine all the irreducible connected components of the variety of polarized nodal K surfaces. And not only enumeration, but also to explain the incidence relation. And the idea, the theorem is that these components are in bijection with the isomorphism classes of some associated binary code, which I will call K prime. So this is like German code, this is K. So what is the strategy is the following. We define these binary codes as the quotients of L prime divided by L, where L prime is the saturation of a certain lattice generated. So let me, I don't like anymore the way it's presented. So let me go to the board. So I have some surface, like a K surface, and I have these nodes. This is X, and then you take the resolution and you blow up. And here, let me do it for surfaces. The inverse image of a node is a curve, node Pi, that is on the resolution X tilde. There is a rational curve, which is isomorphic with E1, with E1 squared is -2. And so HN is the lattice generated by the hyperplane class plus all the curves EI. And this is contained in the second cohomology group of the resolution X tilde with values in C. Okay? So whenever you have a nodal surface which is polarized, you have here is the hyperplane class. And then you have the class of these -2 curves. And this is contained inside there, but this lattice here, L, is not saturated. So the quotient of this by this has some quotient. So L prime is the saturation, which means it is L intersected. Sorry, it's L tensor Q intersected with H2 X tilde Z. So there are elements which are integral, but only a multiple is in L. So L prime is primitively embedded. So this one says that this is a primitive embedding. And it turns out that K prime is defined as the quotient of the saturation divided by L. Okay, so conceptually, it is quite simple. There are certain curves, certain divisors that you see. these ones. But then there are some other hidden divisors, which are just the ones in the saturation. And the way to determine the saturation is to describe the quotient K prime. And this turns out to be a binary code. Okay, so my idea is to use the beam representation, but somehow to leave, I hope everybody can read, to leave the essential ideas for later. So this is the key point. So, so the strategy is the following. I given, for instance, a nodal K3 surface, K prime is defined as the quotient L prime over L, where L is the saturation of the lattice L generated by the hyperplane class H and by the classes of the -2 curves, which are in the cohomology of the resolution. And of course, if it is a K3 surface, this will be called the K3 lattice lambda. So, at a certain moment, to understand these components, the first thing is to do some algebra, some quantity theory, and classify all the possible potentially occurring codes K prime. So we first classify these K primes, these codes. K prime determines a lattice L prime, and then comes the question whether this lattice L prime doesn't admit a primitive embedding in the K3 lattice. That's the second step. One has to determine when does the associated lattice admit a primitive embedding in the K3. Now, as I said before, we want to understand conceptually everything. And to do this, the key idea is the concept of shortening over code. So in a sense, because I said before, what I don't like is computer list. So for the human brain, when we're talking about people or about families, the thing which we really like is a genealogical tree. So like for quartic surfaces, so if you are religious, there is Adam in the beginning, but since we are not religious, there is Kummer. So the Kummer code is the code of a quartic surface AP3 with 16 nodes. After that, they are the descendants. There is one here, here, I forgot how it is. At a certain moment, it becomes like this, big genealogy tree, but there is some more, and you end up like this. So there is like a genealogical tree, and the concept of descendants has so we have here a component of Kummer surfaces which are quartics with 16 nodes. Now, if you go down, the relation is geometrical. Geometrically means partial smoothing. So here I have a quartic with 16 nodes, and then I decide I smooth one node, and I get 15 nodes. And there's only one component. Then here you smooth 2 nodes and so on. So the level is the number of nodes. And however, there is a bijection between codes and components. For the components, geometrically, you have the partial smoothing, but in shortening theory, this partial smoothing is equivalent to the concept of shortening. And okay, even if this is a quite trivial, shortening means the following. A code is a space of functions. Okay? And now, if a function, you take a function defined on a set, then you take the functions in this vector space with support in a subset. That's a shortening. So somehow the lucky discovery of our findings is that I want to see whether one stratum is in the closure of another. That's equivalent to say that you get a shortening of the corresponding code. And in the quartic case, we are lucky, we get all the shortenings of the Kummer code. Okay, so let me proceed generally. I can consider hypersurfaces of degree d. So f is a homogeneous polynomial of degree d, and I take the zero set. And I assume that x has hypersurface in P capital N, which will be, I'm sorry, I'm not capable of using the pointer, but I think you can read that we are in P capital N, and the hypersurface has dimension small n, and assume that the singular locus is a finite set, and it is a node if the quadratic part of the Taylor development is of maximum rank. And so nodal hypersurfaces are the ones such that all the singular points are nodes. And this is a quite general, more general thing of study. So the easiest example historically is in P3, the KD cubic. It's given by the zero set of the third elementary symmetric functions in X. And this is an invariant paper notation, and it's quite easy to see that the singular points are exactly the four coordinate points. And these are nodes. And in fact, in the first coordinate point, we have x0 different from 0, so we ask to find coordinates setting x0 equal 1, and then the first term in the first three terms have order 2, and they are x1, x2 plus x1, x3 plus x2, x3, and this is a rank-free quadratic. So this is a node, and you have 4 nodes. So the study of the cubics was one of the main achievements in the mathematics of the 1800s. And in fact, if a cubic has at least 4 singular points and is normal, doesn't have infinitely many, then it's projectively equivalent to the KD cubic. So what I want to point out is that everything has been known for cubic surfaces since about 170 years, but for quartic surfaces, what I've explained to you is new. And one can define the nodal severity variety, F like family, of hypersurfaces of dimension n, degree d, with number of nodes equal to mu, is some locally closed set. Why is it called nodal severity variety? Because in the case of dimension 1 of plane curves, where in this case you have to add the hypothesis that X is reducible, it turns out that everything is now known, the severity variety of the 3D curves with new nodes is non-empty if and only if nu is any number between 0 and the geometric genus of the curve, d minus 1, d minus 2 over 2. And this is smooth and connected. In fact, this was an assertion by Severi, was made in the appendix, Anhang F of his book on algebraic geometry, but this was an incomplete proof. And it was rescued only more than 60 years later by Johannes and others. And now we look at the Severi varieties in higher dimension, and that's hard. So this is something to give an idea, like we have this genealogical tree, but what we really are looking for is like a stratification of the space of hypersurfaces. So let's take a trivial example. You take diagonal conics, sum ai xi squared equals 0. The parameter space is a projective plane with coordinate a0, 1, 2, and the one nodal diagonal conics are just the ones such that the determinant is 0. And so you have 3 lines, but for the coordinate points P1, P2, and P3, you get double lines. So this is somehow a picture. We understand conics. With a simple picture, we can also explain it to students. And we would like to have a similar picture in general. Well, that's hard, but as a dream, we would like, would be wonderful if we could understand similarly the stratification given in the space of polynomials of 3D by the Severi varieties, and more generally by the singularity. Up to now, we understand quartics and cubic surfaces. Already for cubic hypersurfaces, there are interesting open questions. So, framing somehow the basic questions, which is wide open already for dimension 2. So, when is this variety non-empty? What is the maximum number of nodes that nodal hypersurface of the 3D can have? We call it mu and d. So this is a maximal mu such that you have a nodal hypersurface in real nodes. Can this number be determined explicitly? When, for which nd, we have no gaps. So f and d, the nodal Severi variety is non-empty for all number of nodes, smaller than maximum. When is this connected, irreducible, smooth? How to determine the components? And another interesting question is, everybody, this is sort of understood, that the nodes are the simplest possible singularities. But is it true that the maximal possible number of nodes is the maximum number of singularities? Completely open question. Well, we know something for surfaces, as I said, in low degree. For surfaces in P3, at least we know mu of d, mu2 of d. So for a plane, of course, smooth, quadric. If isolated singularities, a quadric is at most one singular point, the cubic at most 4. For degree 4, the maximal is given by the Kummer surfaces, which have 16 nodes. For the quintics, 31 nodes, the Togliatti quintics. And for the sextics, there is an example obtained by Barth. And well, for d equals 3, we know that if it's 4 nodes, it is really the 4 nodal kd cubic. Now, the number, it's a matter of taste, It was actually found by Schlefly, studied by Cremona, who gave the planar representation. And for degree 4, there are the 16 nodal Kummer surfaces, and for degree 5, there are the Togliatti quintics, and Boville proved in 79 at the Angers conference. Some people were there, he was there. And he showed that mu of 5 is just 31. And in the case of degree 6, Jeffrey Ruberman, and later in a simple way, using some ideas by Johnny or Pinnacle and Tonon, showed that the maximum is 65. So we know something, at least the bounds. But what about the components? And there are no gaps in dimension for surfaces of degree up to 6. This was done by Ron in 1886, and some results with Ceresa and with 6, but even for degree 5, there are no gaps, this new result. So for each number of nodes between 1 and the maximum, there exists a nodal surface of degree D with precisely 2 nodes. For cubics, everything is known. Now, let's go to the case of quartic surfaces. And this was completely open until recently. And I was just able to classify the reducible components of the variety of nodal surfaces of degree 4 with new nodes. And as you see from the picture, for 16 nodes, there is only one family, but the situation becomes complicated. So let me explain at least the result of nodal quartics. So if Y is a nodal quartic surface with new nodes, then we know that mu is at most 16, and I let Y star to be the smooth part. And there is a theorem that the fundamental group of the smooth part is finite and is just Z2 to the K in the case where mu is at most 16. It is isomorphic to the smaller binary code, which is in turn determined by its dimension. Whereas for the quartic surfaces, the fundamental group is the semi-direct product of Z to the 4th extended by Z mod 2. And this is just because the double cover, there is a double cover of the Kummer surface ramified in the 16 nodes, and this is principally polarized surfaces. And one can describe the so-called Kummer codes. So I should say that there are two codes. There is a code K, which is contained in the direct sum of Z mod 2 times the EI, and this is contained in K prime, which is contained in the direct sum of Z mod 2 EI plus Z mod 2 times H. So there are actually two codes. Okay, so this is the result. The subset of the nodal severity variety of quartics with new nodes and the fixed binary code K prime is smooth and connected. Moreover, as I was hinting there, the possible codes appearing are exactly all the shortenings of the extended Kummer code. So the shortenings up to isomorphism. And moreover, a component is in the closure of another if and only if the number of nodes is greater and the second code is a shortening of the first. So you see, this is from this follows an explicit classification and the table, and you can use it, but the result is conceptual. And then follows a classification. It's interesting that for quartics, if the number of nodes is between 0 and 5 or between 14 and 16, there is exactly one irreducible component. But like in this genealogical tree, if nu is between 6, 7, and 13, there are 2, 3 components for number of nodes 8 and 9. And for nu equals 10, you have 5 irreducible components. So we have a stratification made of 34 strata, where each stratum is in the boundary of another if and only if the corresponding extended point admits the other as a shortening. So, at least for quartics, the dream of understanding this stratification is achieved. Now, I need to recall some basic notions of ocurring theory. So, let me do a very quick crash course on binary codes. So, coding theory. Given a field, an F linear code is an F vector subspace K of a vector space of functions on a set. So let me put it here. So here's codes. This is not, sorry, try to see whether this is moved right. So a code K, binary code, is contained in the functions with values on the field with 2 elements defined on some set S. And 2 codes are isomorphism. This means that there exists a bijection between the corresponding sets carrying one code to the other. Now we come to the trivial but very important definition, which I therefore will bring to the board. So we have functions defined on a set S. So assume now that N is a subset of S. Then the shortening is nothing else than the functions in the code which have support on N. So this is a very easy linear algebra definition. And so the shortening is intersection of just a subspace of functions with support in N. And what is the length of a code is the cardinality of the union of the supports. You have functions on the set S, but I mean, they could really be 0 outside a certain subset. So N is just the cardinality of the union of the support of V for V in K. This is called the effective length. The weight of V is just the cardinality of the support of V. So the advantage of a binary code is that, well, this is like the Boolean algebra of sets, because the function has values 1 or 0, and then you take the support is the points which where the function has value 1. So these are characteristic functions of a set, and in fact, the addition for vectors corresponds to the symmetric difference of sets. And the minimum weight is the minimum of the weights, and the dual code is very important is the perpendicular subspace to K. There is a natural scalar product on the functions defined on S, and so there is a dual code. This is important because somehow coding theory was developed by Henning, and Henning developed the Henning code, which is rather complicated. But people who are historically attentive, they call it the dual Henning code, but the dual Henning code is very simple, and I will explain it now. It's just called the simplest code, and I call it, when I give a lecture on linear algebra, the biduality code. So the simplest code says the following, is that K maps gives, this is just, gives some functions defined on the dual of K minus 0. So K is the dual, K is dual to K dual, and so it gives linear functions on K dual, but of course on the origin, the value 0 is uninteresting, okay? And this has the advantage that the weight is just 2 to the K minus 1. Because if the dimension is K, you have 2 to the K elements, and the value of the linear functions is a half of the time 0, and a half of the times is 1. So this is the biduality code, and is called also maybe the simplex code. And the dual of these is the Henning code. So somehow in coding theory there is some linear algebra to be done. For instance, I discovered that they don't use the Radon duality. There is an elementary Radon duality for projective spaces, and this is. There are some results which are folklore, but I mean, you can explain it in 2 lines. Now, McWilliams was the one who associated to a code the function called weighted numerator. Is a polynomial whose coefficients AI is the number of vectors of K with weight equal I. And the famous McWilliams identity relates the weighted numerator of the dual code. So the way this is the weighted numerator for the dual code is obtained for the weighted numerator for K by this simple formula. And I think that Johnny Wall, I think, was the one who gave a very simple proof of some estimate for sextic just using the Williams identity. And this, of course, is an equality of polynomial is equivalent to the series of identities, which are very, very powerful. And a very simple result was obtained, I think, in the 90s or late 80s by Arrigo Bonzoli. Well, he didn't give much for the people in combinatories, but he really gave very nice results, which you can prove yourself once you know. He said, if you have a code where the vectors have only one weight, then it is essentially obtained from the simplest code. Essentially means the following, that you get a simplest code as a functions on S2, and then your set can be written as a Cartesian product as 1 times S2, and to a function V in the simplest code, you associate a function of X and Y, which is just the given function of Y. So, due to the McWilliams identity, the codes with only one weight are understood. And there is a lot of results about codes with 2 weights, 3 weights. Unfortunately, in our case, I had to work because I wanted to do theorems, and there were codes with up to 5 weights, which is a little bit outside of the technology. So, what is the code of the Kummer? So, linear functions yield the biduality code. Now, next to linear functions, there are polynomials that could be up to 2. So, if A is an affine space of dimension m over the field with 2 elements, so A is non-canonically identified to have 2 to the n, the first Reed-Muller code is the space of affine functions. So a constant plus a linear function. The second Reed-Muller code is the space of polynomial functions of the linear function. This is too large. The Kummer type code is very simple. You just take the first Reed-Muller code and you just add one non-degenerate quadratic form. And if you know theta functions, you see that somehow the condition that a half period belongs to the 0 of the theta functions. This is given by this quadratic function. That's why you get 16, the number of theta characteristics and just. So the standard code, Kummer code, is obtained for n equals 4. So you have 16 elements, you have a function with 16 elements, and you get this Kummer code. And now something we never do in linear algebra because time is never enough, but it's interesting. We never do quadratic forms in characteristic 2. But in fact, there is a linear canonical form that you can just write Q as a sum x1, y1 plus x2, y2 plus xa, yh. Because there are some normal forms, but modulo, there are 3 normal forms, but essentially modulo constants for xk plus 1 squared, since you have a finite field is a linear form, so you can really reduce to that. So anyhow, this is not relevant. I mean, but it's interesting. Everything boils down to linear algebra over field with 2 elements, where you have the concept of elliptic and hyperplane quartics. And okay, so this is the theorem. If you have a nodal surface, so now, I want to explain what is the relation with topology. The topology of the smooth part. So if you have a nodal surface in P3, the code, the strict code, is dual to the surjection. You see, the homology of the smooth part is a quotient of the local homology around the nodes. The nodes are just C2 divided by plus minus 1. So you get like, the first homology is just C2, because that's a local fundamental group. So the meaning, there is a geometric meaning that this small code is just the dual of this surjection. If you blow up Y at the nodes, take a hyperplane section, then you have this extended binary code, which I already wrote somehow, and this determines the saturation inside the homology of the resolution of the lattice generated by the curves -2 curves and H. And this is precisely the saturation. You just take, it's generated by L, and then you take 1/2 of the combinations of AI plus BH, where this modulo 2 is KPI. So essentially, there is another way to describe the code to say that you take the linear combinations which are divisible by 2. And this is an important information to determine the weights of the codes. So determining the weights of the codes is something which is really the hard part. This requires commutative homological algebra, and it's really hard. The rest is easier. But this was done. Now, let me finish with the K3 circles. So here we apply the Torelli. So for Y, we have this lattice contains the sublattice generated by this curve and H. And the extended code determines the saturation. In the 70s, Nikulin developed a theory of primitive embeddings of lattices, generalizing results of Miller and others to the non-unimodular case. And Nikulin's results give criteria for existence and unicity of such embeddings. The only thing is that, unfortunately, Russian was translated in English by someone expert, and there is some stupid misprint. I lost a lot of time because the word student says there exists a unique primitive embedding, which in English means there exists an embedding and is unique. But in Russian, it meant there exists at most one primitive embedding. This is the problem of translations. Not in translation. So there are two theorems, one about existence of embeddings and one unicity, and unicity is easier. And these results are very useful for K3 surfaces because even a potential called K prime, you determine K prime, and then you ask when there is an embedding. So for a quartic surface, so the first step, we determine the potential extended code K prime, the potential saturated lattices, and then in this case, Nikulin's theorem says that if there exists a unique primitive embedding, this is unique. And the existence, we can dispense with it because I prove that all these codes are the shortenings of the Kummer codes. Now there is a theorem by Burns involved saying that quartic surfaces are unobstructed. So given a Kummer, I can take whatever partial smoothing I want. And so this shows that all the shortenings of the so for other degree K3 surfaces, then I have to work hard. And now I dispense with writing the equation from Torelli. So you fix this embedding, and then you impose the conditions that these elements of the lattices are of type 1. These are very simple equations, but they give two components which are exchanged by complex conjugation. And I want to prove that it is only one. And so the result is that we get a single connected component if we find such a nodal surface which is real. And here I use some very simple Kummer quartic. So every algebraic geometer knows that the Kummer surface is obtained from a principally polarized surface divided by plus minus 1. But you would like to say a simple equation, and it's very simple. You take the sum of the xy squared minus 3 times the sum of the fourth power. Now, what is nice here is that the 16 singular points are just, this is a symmetric function, and you just get the points of the type 0, 1, and then plus minus 1, plus minus 1. And, well, you get 4 points for this, and then you decide how many zero, where is the 0, so you get 4 times 4, 16 points. And this is quite nice, this quartic is defined over the reals, actually over the integers. The singular points are defined over the integers, so this is also good for doing the specialization to whatever is P, and it has this nice symmetry. And okay, this is something which I already said. A nodal hypersurface is unobstructed if the singular points impose linear independent conditions on the homogeneous polynomials. Unobstructed means that whenever I have a subset n prime of the set of nodes n, there is a small deformation smoothing all the nodes. And so unobstructed is the key result of the formation theory, which puts a link between geometry and coding theory. If y prime is gotten from smoothing the nodes in n minus n prime, then the code of an y prime is the n prime shortening. And okay, so it turns out that all codes of nodal quartic surfaces come from partial smoothies of the Shafarevich quartic. And yeah, whenever you get smoothing again, you get quartics which are defined over the reals, and the nodes are defined over reals. And okay, here I briefly mentioned what is used. The codes K prime, they have the weights only 8, 16, and 7. There are only 4. In this case, there are only 4 type of weights. And this allows, with some work, to show that these are all the shortenings of the extended movement. And this causes the result for quartics. Now, what is interesting and unexpected is the result for other case surfaces. Again, if the degree is divisible by 4, you get Kummer surfaces extended. And otherwise, you get 15 nodes. And one would like to ask, is it true, like for the quartic case, that there is only one answer in all the specializations? And the surprising answer is no. Here, we look at other cases, surfaces of degree 2 times g minus 1. And now these codes, the codes determine that we have 4 different cases according on the residue class of the degree. The degree is an even number, modulo 8. But here, when you classify the code, you get the lattice, and then you see, does it admit a primitive embedding in the K3 lattice? Here, many people have been using the results of Lipuni, Dolgachev, and so on, but they always use the single case where you have strict inequality. This is the first time that I made my test dirty. I looked at the case for equality, and there is some arithmetic condition for the embedding, and it just says that this condition is satisfied according to what is the congruence class of D modulo 16. And there are also some other sporadic examples, and these are interesting geometrically because if you take, there is some old theorem of Saint-Donat, which says if you have a cadence surface with nodes, you can take a node and you can project from the node, and you get other cadence surfaces in smaller dimension. This procedure gives some exception trendings. So, well, as I said, the surfaces are a miracle because there is this Torelli theorem, and we can really reduce everything to linear algebra or lattice theory. What happens for critics? So, there was a very important remark by Bouville, who says when you get these elements K prime, there is an inequality which says that the weights, the dimension of the codes satisfies certain inequality. And so the potential codes are the ones which satisfy this inequality described by Buffy. For instance, it's easy to show that if you get an element of the code K, its weight, I will call it T, is just the cardinality of what is called an even set, and this is always divisible by 4 and divisible by 8 if this is ever even. And now it turns out, due to some theorem proved by Rubin and also proved together with Casnati, that for a quictic surface, the only possible weight of the vectors are 16 and 20. And with Sandro Vera, recently I proved that if a nodal quictic has an even set of cardinality 20, then the number of nodes is at most 28. And this is related to a certain representation of this even set of nodes related to a web of quartics. Now, the inequality comes from application of the Bezout theorem for the base points of this web of quartics. So, if you get cardinality 20, then you get at most 28 nodes, and you get an irreducible component of this nodal variety. So this is based on some earlier work by Sandro Vera about prime varieties. And from this it follows that a nodal quictic surface has at most 31 nodes, and the quality holds if and only if K is a simplex code. And this is obvious because the only weight is 16, and we can apply Monisoli's theorem. So this is a much simpler proof of this theorem. That these surfaces with 31 nodes exist was proven in 1940 by Togliatti, and it was using an important method, which is the method of projections of cubic hypersurfaces from a linear subspace. In this case, you take a cubic hypersurface in 5, which has 15 nodes, and then you take a general line containing it. And then the projection gets 15 nodes from the 15 nodes of X, plus 16 other nodes, which come from the representation as a determinant of a 3 by 3 matrix of polynomials. And the method of Togliatti didn't verify everything, and an explicit equation was found by Bart, and recently Stephen Kaplan and Capote were cooperating with some parts. There are 4 articles, one I gave the surfaces in myself, and they found some, well, now they use computers, some beautiful determinantal equation. This is an explicit equation of a quintic. It's a determinant. You see, the first entries are linear forms, whereas M1, 2, 3, M2, 3 are quadratic forms, and in the corner to the right down, you have the Cayley cube. And this explicit has 31 nodes and no other singularities. So this is the most beautiful explicit equation of a quintic with 31 nodes obtained from the Togliatti method, which I verified, the assumption. And the result for nodal quintics is that the Togliatti, the family of quintics with 31 nodes, this is an irreducible family. Now, so why is this important? So for me, this was one of the motivations. So the idea is very simple. You have a cubic hypersurface. You have a cubic hypersurface with files, okay? And the point is that if you have a node, X has degree 3, and then the Taylor development is Q2 of X plus G3 of X equals 0. So feeding a cubic with a node, and you take coordinates such that the node is X equals 0, gives a Taylor development. And now to this, you associate the Cantor surface of degree 6, which is Q2 of X equal G3 of X equals 0. So my motivation for studying more general Cantor surface was to show the irreducibility of the family of the liquids. These are Cantor surfaces of degree 6, and once this was done, and there are some results. All the codes of nodal quintic surfaces are known, either shortenings of the bipartite code or shortenings of this unique two-dimensional code with two code words of weight 20, but there is one case which evades our present answer. We don't yet know all the answer for now. There will be, I can leave the transparency about sextics. Sextics is really like fairy tales. There is some connection with special graphs and codes and a lot of computer algebra, but I think I already abused all the notation sufficiently. Thank you.